One company controls 90% of the world's most advanced chips. Not most, not a majority, 90%. And a 2% ordering mistake nearly collapsed global civilization. In 2021, automakers couldn't build cars. Hospitals waited months for medical equipment. Game consoles sold for 3 times their retail price on secondary markets. All of it traced back to a single miscalculation. A rounding error, really. But here's what that crisis revealed. Something the industry had been quietly building for 30 years. A supply chain so concentrated, so geographically fragile, that a single earthquake, a single political decision, a single factory fire could end the modern world as we know it. This is no tech, and this is the truth about chip wars and supply chain fragility. For most of the 20th century, the story of global manufacturing was a story of spreading risk. The logic was simple. Build your supply chain across many countries, many suppliers. If one failed, another stepped in. Redundancy was the whole point. Economists called it comparative advantage. Countries specialized in what they did best, and global trade stitched it all together into something resilient. And semiconductors, we assumed, followed the same logic. Multiple manufacturers, multiple countries, multiple nodes, a genuinely distributed system. Surely no single failure could bring it all down. I believed this too. It seemed obvious. The chip industry was global, sophisticated, worth trillions of dollars. Of course it had built-in redundancy. Of course it had backup plans. Then I started looking at what the industry actually produces and where. And the picture looked nothing like what I expected. The resilience was an illusion. The redundancy didn't exist. Not where it mattered most. Let's go back to early 2020. The pandemic hits. Automotive manufacturers look at their sales forecasts and make a reasonable call. People aren't buying cars during a global lockdown. So they cancel their chip orders. Not all of them, just a small reduction. 2 to 3% off their projected demand for the year. 2 to 3%. Here's what they didn't account for. The rest of the world was also at home, buying laptops, buying tablets, buying game consoles, upgrading home office equipment. Consumer electronics demand didn't drop, it exploded upward. Chip fabs, which operate at near-perfect capacity all the time because the economics demand it, simply redirected their production. The automotive allocation disappeared into consumer electronics orders within weeks. When car sales rebounded faster than anyone predicted, automakers went back to their chip suppliers and found nothing available. The fabs were fully booked, months out, in some cases, years out. The result? Ford shut down production lines. GM idled plants. Volkswagen, Toyota, Stellantis, all of them sitting on half-finished vehicles, waiting for microcontrollers worth a few dollars each. The automotive industry lost an estimated $210 billion in revenue. Not from a cyber attack, not from a natural disaster, not from a factory fire or a geopolitical crisis, from a 2 to 3% demand miscalculation at the start of a pandemic. But this raises the obvious question. Why was a system worth trillions of dollars so brittle that a rounding error could shatter it. To understand why, you need to understand what it actually takes to manufacture a modern chip. A chip at the leading edge today is built at 5 nanometers, 3 nanometers, 2 nanometers is coming within the next few years. For context, a strand of human hair is roughly 23,000 times wider than a 3 nanometer transistor. We are patterning features onto silicon at a scale smaller than most viruses. To etch features that small, you need a machine that produces light at 13.5 nanometers, extreme ultraviolet light. Light so short in wavelength that air itself absorbs it. The entire optical path has to run inside a vacuum. There is exactly one company on Earth that makes these machines, ASML, a Dutch company headquartered in Veldhoven in the southern Netherlands. Their EUV lithography system is one of the most complex manufactured objects human beings have ever assembled.
Each machine contains over 100,000 individual components sourced from suppliers across the globe. It costs between $150 and $200 million per unit. And ASML produces approximately 30 to 40 of them per year. 30 to 40 machines per year for the entire planet's semiconductor industry. That constraint, physical, economic, and rooted in the fundamental physics of light, is why chip manufacturing concentrated the way it did. It's not that TSMC got lucky. It's that the economics of leading-edge fabrication reward whoever gets there first and punish everyone who tries to catch up. Building a leading-edge fab isn't just expensive. It requires decades of accumulated process knowledge, thousands of specialized engineers who take years to train, relationships with hundreds of suppliers across dozens of countries, and allocation from those 30 machines per year, which are already spoken for years in advance. TSMC didn't dominate because of luck or geography alone. They dominated because they invested earlier, deeper, and more consistently than any competitor. For 30 consecutive years, every process generation, every node shrink, they pushed further while others pulled back. And by the time the rest of the world noticed how concentrated the industry had become, the physics made it nearly impossible to catch up quickly. Each new generation of chips doesn't just require more money. It requires more specialized knowledge, more precise equipment, and more of those 30 machines per year that ASML is already struggling to produce fast enough. The concentration wasn't a conspiracy. It was the natural outcome of a technology that rewards scale, punishes redundancy, and makes catching up exponentially harder with every passing year. Here's where most people get the story wrong. The common assumption is that blocking China from accessing ASML's EUV machines effectively froze China's semiconductor ambitions, that the export controls worked, that the choke point held. They didn't. Not entirely. In 2022, China's SMIC, its largest domestic chip maker, was reported to have achieved 7 nanometer class chip production without a single EUV machine. They did it using older DUV lithography, deep ultraviolet machines that ASML had already sold to China before export controls tightened. And they applied a technique called multi-patterning, exposing the same silicon layer multiple times with precise offsets, stacking exposures to achieve finer features than any single pass allows. It's slower, it's significantly more expensive per wafer, and yields, the percentage of chips on each wafer that actually function correctly, are substantially lower than what TSMC achieves on equivalent nodes. But it worked. China built 7 nanometer class chips anyway. The Huawei Mate 60 Pro shipped with one of them inside. a phone that wasn't supposed to exist, running silicon that wasn't supposed to be possible. This is the uncomfortable truth about the export control strategy. It slowed China down. It raised their costs. It reduced their yields. But it didn't stop them from making progress, and it revealed something important about the nature of technological choke points. They're more porous than they appear. Given enough time, enough capital, and enough engineering talent concentrated on a single problem, constraints get worked around. Maybe not elegantly, maybe not efficiently, but they get worked around. The EUV monopoly remains real and significant. ASML's machines are still years ahead of anything China can produce domestically. The gap in yield and efficiency is meaningful. But the assumption that a single export control on a single category of machine could freeze an entire nation's technological trajectory, that assumption was wrong. So where does that leave us? In 2022, the United States passed the CHIPS and Science Act. $52.7 billion allocated to rebuild domestic semiconductor manufacturing and research. The largest industrial policy investment the US had made in a generation. And industry analysts estimate that building a genuinely competitive leading-edge fab ecosystem, one that could meaningfully reduce dependence on Taiwan, would require $500 billion or more, sustained over a decade. 52 billion against 500 billion.
That gap is the real story of chip geopolitics. Not the speeches, not the ribbon cuttings. The gap between what was funded and what would actually change the physics. The CHIPS Act matters. Intel is building fabs in Arizona and Ohio. TSMC itself is constructing facilities in Phoenix. Samsung is expanding in Taylor, Texas. These are real investments with real long-term consequences. But the physics of leading-edge fabrication doesn't respond to political will on a political timeline. Each new generation of chips requires years of process development, billions in equipment procurement, and the kind of institutional knowledge that takes decades to accumulate. Knowledge that can't be hired or legislated into existence on an election cycle. Meanwhile, Taiwan remains the center of gravity. TSMC continues to push toward 2 nanometers and beyond, and the Taiwan Strait, the body of water separating Taiwan from mainland China, roughly 130 kilometers wide at its closest point, remains one of the world's most geopolitically sensitive regions, its importance rooted not in contested claims over the waterway itself, but in the unresolved question of Taiwan's political status and the extraordinary concentration of semiconductor power sitting on one side of it. This is the fragility we built. Not through malice, not through incompetence. Through 30 years of individually rational economic decisions that, in aggregate, created a single point of failure for modern civilization, and then bet the entire global economy on its continued stability. The 2021 chip shortage wasn't primarily a warning about demand forecasting. It was a warning about what happens when efficiency becomes the only goal. When every redundancy is stripped out because redundancy costs money, and the market never prices in the risk of catastrophic failure. Every decision that concentrated chip manufacturing in Taiwan made economic sense at the time it was made. TSMC was better. TSMC was cheaper. TSMC was ahead on every metric that mattered to a quarterly earnings report. So the world gave TSMC more business, and more, and more. Until one company, in one country, on one island separated from a geopolitical flashpoint by a strait roughly 130 kilometers wide, controlled the technological future of 8 billion people. This reminds us that resilience and efficiency are not the same thing. They are often opposites. And for 30 years, every time we had to choose, we chose efficiency. But the chip supply chain isn't the only place we've made that trade-off. I'm here to help you know the infrastructure that runs the world. What other single points of failure are hiding in plain sight? Tell me in the comments. See you at the next node.